Hey, it's Alex from Canon Academy, and today I'm going to go over the stability of carbocations, anions, and radicals. Now, this is probably one of the most important things in OChem 1. With it, you'll be able to do E1 reactions, you'll be able to do free radical halogenation. It'll go on till OChem 2. It's one of the most important things you're going to learn because it just applies to everything. I've probably written this order down right here about 1,000,000 times, and you probably will too. Anyhow, cations are positive carbon atoms, so carbocations. So that's when one of our structural compounds have a positive charge in the structure, and this is the order of stability. Now this B degree sign over here refers to the benzylic position. That you know what a benzene is, of course, from our functional group videos. It could also look like this as well, and sometimes you'll see it abbreviated pH. Anyhow, I'm going to use the most common one you'll see, but the important thing is this is a benzylic position, so it's different than a benzene. What it means is this is one carbon next to the benzene ring. Why is this so stable? Both it and the allylic group are both stable because of resonance. Resonance is a huge thing on stability. That's why it's one of the most important concepts you'll learn. That's why they hit it right out the gate in the beginning. Now, this is a ton of resonance structures. I'm sure you'll have to draw them out eventually. What it looks like is this double bond here ends up moving to that position to move that carbocation, so you can actually have a group here with a positive charge. And then once it's there, so if I drew that out for you, you have the positive charge there. And then you can make another structure by moving this one. So now the positive charge goes where the bond used to be. This is gone, and then the bond's moved over one. Then you can do it again, and each time you'll get a different structure. So we can do this, the positive charge, and we can do it one more time to get things back to where they started. I believe there are 5 resonance structures there all in one, making this extremely stable because you can share the load of the burden of carrying that positive charge. Now our next group we can do, let me just leave it here under the B here, benzylic next door. Also, the allylic one now, allylic is next door to a pi bond. So it's a carbocation next to a double bond. This one doesn't have as much resonance structures, just 2. There's the first one here, and then if I followed it over, you have your second option with it moved over here. That allows it to share this positive charge among 2 carbons. Also very stable, just not as stable as having a ton of resonance structures as to the left. Our next 3 are stable because of conjugation. So tertiary, secondary, and primary, all due to conjugation. Now, conjugation is basically the stabilization of that positive charge. So this will show a tertiary carbon right there. And I'm going to go ahead and write the CH3s here. And then for this one, I'll draw the H's out. Now for each one of these, even though this doesn't really have any strong hydrogen bonds, it still has a partial negative here. Very, very small partial in the center. That's because the electronegativity of hydrogen is about 2.2 and carbon is about 2.5. So all the dipole moments are slightly going towards carbon, giving it a tiny little negative charge. And that's true for all the carbons around this positive charge. What this means is all this cloud of negative charge around that positive charge will stabilize it, make a nice little spot for it to rest in, and it'll basically keep it much more stable than only one could. This is the opposite for negatively charged things, because we know that positive charged things attract to negative, negatives repel each other. That's why when you talk about anions, this order is slightly different in stability. So let's redraw our anion stability. And because they're the same basic thing, I'm just going to copy and paste this. The only difference is we switch the 1 and the 3 because we want it to touch the negative charge as least as possible. That's because if we put a negative charge there, they would repel each other. Now let's do a primary carbon, C to CH3, and H, and positive. So here we still have a partial negative there, but it's not a lot as last time. So it's not nestling that positive charge as well, so it's not very stable. But this is good for a negative charge because it's not repelling it as much as 3 attacking it from the other side would. So instead you only have 1, which makes this the most stable negative charge, or anion. The last two are based on the breaking of resonance or messing with those nice structures. So vinyl and aromatic are kind of the opposite of benzylic and allylic. So vinyl is if you put a positive charge on those double bonds. This is really weird. Shouldn't really happen. It's way unstable. The only thing more unstable than it, in fact, is the aromatic, which is what you would normally want to do if you heard benzylic cation, and that's put a positive charge on a benzene ring. This is a lot worse because you're messing up that resonance. You're kind of making the negative charge stick more towards this, and it doesn't really like that at all. Okay. Anyway, that's your stabilities here, and I'll just redraw them here for reference. It's important to note that the radicals are the same, the carbocations, because they use the same mechanisms, resonance and conjugation. So really you just have to memorize, you only really have to memorize this right here. You will write it out a ton, so it's really useful. And the only thing you have to do to remember the anions is to flip the 1 and the 3, as shown here below.